Hey everyone, have you ever really stopped to wonder what the universe is made of? I mean, at the most basic, fundamental level. Well, today we're diving into a field that sounds like it's straight out of science fiction, but it's actually the operating system for our entire reality. We're talking about quantum physics. So, when I say quantum physics, what's the first thing that pops into your head? For a lot of people, right, it's these super bizarre, confusing ideas, stuff that feels totally disconnected from our day-to-day lives. But is that really all there is to it?
Oh, not even close. The truth is, quantum physics isn't some far-off abstract theory. Nope, it's the hidden engine that's literally powering everything around you. So come on, let's pull back the curtain and really see how this whole thing works.
Okay, first things first, let's get one thing straight. This stuff isn't just happening in some high-tech lab somewhere. No way. From the phone that's probably in your hand right now to the sunlight hitting your face, you are interacting with quantum physics every single day. And you probably don't even realize it.
You know, Caltech puts it perfectly. Quantum phenomena are all around us, acting on every scale. Now, obviously, you're not going to see a baseball suddenly start behaving like a wave, right? But these fundamental rules, they're always at play, under the surface. They're the missing pieces that fill in the gaps of older physics, explaining everything from the chemical reactions happening inside our bodies to the light traveling from stars billions of miles away.
So where did all this crazy stuff even come from? Well, you have to go back to the early 1900s. Scientists started seeing things, making observations that just didn't fit with the classical rules of physics. Nothing made sense. And what they found out was that at the tiniest, most fundamental levels, the universe isn't smooth and continuous like we thought. It's something else entirely. And this discovery, it led them to the core idea of quanta. Think of them as tiny, individual packets of matter and energy. In fact, that's where the word quantum comes from. It's Latin for how much. A perfect example is light. We think of it as a continuous stream, but it's not. It actually delivers its energy in little bundles called photons. You can have one photon or two photons, but you can never have 1.5 photons. It's a simple idea, but man, was it revolutionary. And this one idea, it totally blew up our old picture of the atom. We used to imagine electrons as these little planets zipping around a nucleus, right? Well, the quantum model changed all that. Now we know an electron exists in a cloud of probability, this fuzzy region called an orbital. And here's the really weird part. It can never ever be found in the space between these orbitals. It just disappears from one spot and instantly reappears in another. No travel time, just gone and then there. Wild. Okay, so this whole new way of looking at the universe is built on a few key ideas. And I'll admit, they are pretty mind-bending. But let's try to break down the 4 big rules that basically run this whole strange quantum show. All right, rule number 1, wave-particle duality. So early experiments showed that tiny things like light and electrons were kind of shifty. Sometimes they'd act like a solid little particle, like a tiny billiard ball, but other times they'd act like a spread-out wave. And the weirdest part of all, what they decided to be, it depended entirely on how you tried to measure them.
So what does that actually mean? Well, it means they're not really waves, and they're not really particles. There's some new, distinct kind of quantum object that our brains just have a really hard time picturing. We're stuck using words like wave and particle as analogies, but the truth is, there's something else altogether.
Okay, rule number 2 is superposition. Now get ready for this one. It's the idea that a quantum object can be in a combination of multiple states all at the same time. Let's take an electron, for example. It has a property called spin. You can think of it like a tiny little magnet. Well, in superposition, its spin can be both up and down at the exact same time. It's not one or the other, it's both, right up until the moment you measure it.
To try and make that a little easier to grasp, Caltech has a pretty good analogy. Imagine a ripple on a pond, right? But this ripple is made by 2 different waves overlapping each other. That ripple isn't just wave A or wave B, it's a combination of both. Well, a quantum object in superposition is kind of like that, mathematically speaking.
Next up, rule number 3, the uncertainty principle. And this one's important. It's not because our measurement tools aren't good enough. This is a fundamental law of nature. There's a built-in trade-off. The more precisely you know where something is, like an electron's position, the less precisely you can know how fast it's going, its velocity. And the other way around too. You can simply never know both with perfect accuracy at the same time.
And last but not least, rule number 4, entanglement. This is what Einstein famously called spooky action at a distance. It's when two or more quantum objects get linked, and from then on, they behave like a single system. What you do to one particle instantly, and I mean instantly, affects the other, even if they're on opposite sides of the galaxy. And here's where it gets really, really strange. If you measure a property of one of those entangled particles, say its spin, you instantly know the spin of its partner. There's no signal, no message traveling between them. It's like their fates were sealed, linked together from the very beginning. They just are connected. So when you put all these rules together, you get to one of the most famous, most debated, and honestly, most baffling parts of quantum mechanics. The fact that this simple act of looking, or, well, measuring, seems to change reality itself. Okay, let's talk about the famous double-slit experiment. It goes like this. You shoot particles, like electrons, at a wall with 2 slits in it. Now, if you don't watch them, they act like waves, going through both slits at once, and creating this complex interference pattern on the back wall. But, and this is the crazy part, the second you put a detector there to see which slit they go through, boom, the wave behavior vanishes. They start acting like normal little particles, and you just get 2 simple lines on the back wall. The act of measuring literally changed the result.
Now, just to be super clear, this isn't about a person with consciousness watching the experiment. That idea really confused people for a long time. We figured out that measurement is a much better word than observation. Any physical interaction with that quantum system, even if it's just from an automated little detector, is enough to force that wave of all possibilities to collapse into one single definite reality.
So, okay, we've got these incredibly strange rules, right? Discrete packets of energy, things existing in multiple states at once, these spooky connections across space. It's a lot. But all this quantum weirdness, it isn't just some fun thought experiment for physicists. It is the engine behind the technology that powers our entire modern world. Remember that quantum leap we talked about, with electrons jumping between orbitals? Yeah, figuring that out gave us the laser. And learning how to control the quantum behavior of electrons in materials like silicon, that gave us the transistor, that little tiny switch that is the building block of, well, every computer, every smartphone, everything. And now, by learning to control superposition and entanglement directly, we're building the next revolution, the very first quantum computers.
And really, that's the big takeaway here. Understanding the fundamental rules of how the universe works, no matter how strange or counterintuitive they seem to us, is the ultimate resource for innovation. It's how we build the future.
So what's next? What's the next big frontier for quantum science? Well, physicists are now using these very tools to tackle the deepest questions we could possibly ask. Questions about gravity, about the true nature of space and time, and maybe even to find out if everything in the universe is connected in some deep way we can't even perceive yet. The weird has officially become wired, and believe me, the future it's building is just getting started.